We are Group 6, presenting our project Digital Dental Solutions. Our integrated solution includes automatic single crown design, gingival recession measurement, periapical lesion classification, and 3D orthodontic movement simulation. According to the Ministry of Health and Welfare in Taiwan, the ratio of dentists to dental technicians is roughly 10:1. In prosthodontics, temporary crowns are still sculpted manually by dental technicians, which typically takes 1 to 2 hours per case. Gingival recession is commonly measured with a periodontal probe, making it highly operator-dependent and prone to human error. In addition, periapical cysts and granulomas look extremely similar on X-ray images, requiring highly experienced clinicians to interpret. Orthodontic planning also lacks standardized, visualized tools for simulating tooth movement. Therefore, our goal is to combine AI and geometric modeling to create a more automated, objective, and visualized oral health assistance system. 1. Automatic single crown design. We use a statistical shape model, SSM, to build a crown database and generate crowns efficiently and consistently. Our reconstruction accuracy achieves mean absolute deviation less than 0.1 mm, RMSE less than 0.4 mm. 2. Gingival recession measurement. We propose a curvature-based, fully automated workflow that extracts CJ/GM distance from 3D dental models. The measurement error is controlled within 0.5 mm. 3. Periapical lesion classification. We apply NNUNet to automatically segment lesions in CBCT data and combine multiple classifiers to provide a reliable second opinion for clinicians. 4. Orthodontic movement simulation. We construct a local coordinate system for each tooth and simulate rotation, expansion, intrusion, and other movements with collision detection to accurately visualize dynamic orthodontic processes. Previous studies indicate that GAN-based CG models can generate occlusal morphology. SSM provides stable and interpretable shape reconstruction. Our method integrates the stability of PCA-based SSM and the flexibility of deep learning, supported by mesh processing techniques, to form a complete workflow for temporary crown generation. Database construction. Import base crowns and samples, perform ICP plus CPD alignment. CPD ensures point-to-point correspondence. PCA modeling. Compute mean shape and principal modes of variation. Model generation. Use PCA weights to generate deformable crown models. Our platform requires only the target tooth, its opposing tooth, and the SSM database. Within 5 seconds, the system generates a crown prediction. Case 1. Different PCA modes allow technicians to choose crown styles. Mean deviation, 0.243 mm. Inference time, 0.161 s. Case 2. Technicians may adjust the sharpness or roundness. Mean deviation, 0.27 mm. Inference time, 0.149 s. Case 3. Mean deviation, 0.198 mm. Inference time, 0.134 s. Our platform additionally offers crown abutment mesh stitching, enabling same-day temporary crown delivery. Heat map analysis shows occlusal surface, no large error region, stable reconstruction. Lingual surface, evenly distributed errors. Buccal cusps, higher deviation due to natural anatomical variability. Summary. SSM performs well in low variation regions. Occlusal and lingual morphology shows high stability. PCA limits detailed reconstruction in contact areas. Future improvement, integrate deep learning for personalized occlusal detail. 1. Cole et al. Curvature-based CEJ detection improved annotation accuracy. 2022, JS et al. Demonstrated digital gingival measurement feasibility. 2023, Martins et al. Established a digital workflow with higher repeatability than manual probing. All studies highlight limitations of manual measurements and emphasize the advantages of digital automation. Our work continues this direction and moves toward full automation. Using 6 clinical samples from Jiayi Christian Hospital, segment upper and lower arches. Build local coordinate systems for each tooth. Generate standardized cross-sections along the tooth axis. Calculate 2D curvature and detect CJ and GM via regional peaks. Map results back to the 3D model and output PNGs and numerical logs. Compared with previous semi-automated studies, our method measures 14 teeth per arch in 15 seconds, saving 95 to 97% of manual time. Error analysis: most cases fall within plus or minus 0.3 millimeters. A few outliers occur when gingival curvature is complex or when slice angle sensitivity causes local misalignment. Historical context: 1970, a study of 1,600 cases showed traditional radiographs are insufficient for distinguishing cysts versus granulomas. 2021, NNUNet automatically adapts pre-processing and architecture, improving segmentation on medical images. 2024, multi-slice CT texture analysis demonstrated discriminative power between cysts and granulomas. Our contribution: we extend these approaches using CBCT, 16 clinically validated cases from Jiayi Christian Hospital. NNUNet segmentation lesion ROI extraction. Texture features plus grayscale values, SVM, decision trees, and weighted voting for classification. Validation curves show decreasing training/validation loss without severe overfitting. DICE score improves from 0.3 to greater than 0.8. 3D reconstructions show high overlap with clinician annotations, except in areas with metal artifacts or blurred cortical boundaries. Current model performance, ACC, 92.86%. Sensitivity, 100%. Specificity, 88%. Literature indicates, controlled 1 to 5 mm expansion can serve as an alternative to extraction. Diffusion models and GNNs are used to simulate multi-tooth movements. Orthodontic theory emphasizes phase-based expansion, rotation, and intrusion. These motivate our method. Method overview. Model centralization. Use midpoints of adjacent teeth to determine mesiodistal direction. Compute arch plane using PCA. Establish XYZ local coordinate systems for each tooth. Simulation pipeline. Expand tooth position step by step along y-axis. Use BFS-based collision detection. If overlap occurs, move the closer tooth first. Perform ICP-based rotation and translation toward the target. Final buccal movement along local axes to match predicted post-treatment positions. Outcome. The system presents a dynamic 3D animation of the full orthodontic movement path. Future enhancements include dual arch simulation and root level control. We would like to thank our advisor for continuous guidance and professional support, which established the foundation of this project. We also appreciate the clinicians and dental teams for providing clinical annotation, validation, and expert insights. Finally, we thank our classmates and seniors for assisting in discussions, testing, and development throughout the entire research process.